A Lagrange interpolating polynomial is another way to be able to develop a curve that exists through n points and get an n-1 degree polynomial. Instead of using, and remember we use the idea of the area of a triangle and similar triangles to develop the first one, or the linear Newton interpolating polynomial. And then from there, we did some substitutions basically to solve it like a matrix. What we're going to do this time is we're just going to have the idea that if we have n points, we can have a matrix of n-1 degree, and we could just set up our system as a product of matrices. And then we can just do some matrix multiplication to be able to find the undetermined coefficients for each of the powers. All right. So essentially what we're doing is we're just doing a whole bunch of polynomial multiplication, and we're going to be able to, or matrix multiplication, excuse me, and eventually we get, when we multiply it out, we end up with this yi L sub I x. And the question is, what is L sub I x? Well, L sub I x is going to be a product. And whenever we have this pi is really just a shorthand for products. All right. So for instance, if you had, just to show you a really quick one, if you have pi of I equals 1 to 3 of I square, that would be 1 square times 2 square times 3 square, which would be equal to 36. All right. So all we're doing is we're just multiplying out the matrix. And notice that I cannot be equal to j. And that's because, well, if I were equal to j, we'd be divided by 0. Okay, so as we progress through the index, we're not going to have the same numerator and the same denominator simultaneously. All right, so a really basic example. All right, and I typed this out just to show you for a polynomial. Let's say we have 3 points. Let's say 1, 2, 2, 4, and 3, 7. And first we're going to compute L1, or L1, L2, and L3. All right, so we're going to have a second degree polynomial so that we're going to have 3 of these L's. And I want you to notice the patterns of these. It's actually pretty easy to notice the patterns, is that each time as we're multiplying through, notice that each of the products has the same second terms in the difference of the numerator and denominator. All right. Another thing to notice is statically, these all correspond to the index of L that you're finding. All right. So all you're really changing each time is you're just changing the second set, or the second terms in the numerator and denominator each time. The first term stays static. All right, so the first term is always x, that's our unknown, as we build our polynomial, and then the x sub I stays static with L sub I for each of the first terms. All right, so first term stays static, second terms just change in accord with the index. All right, so you just keep going up. You never have x1 minus x1, x2 minus x2, x3 minus x3, because I cannot be equal to j. All right, so we don't ever have those. So that's the pattern that we use. And x1, x2, and x3 in this case, x1 is going to be 1, x2 is going to be 2, and x3 is going to be 3. All right, so we just substitute those directly in, and then we compute, and we just keep doing that, and we just simplify each of our expressions, and this is what we would end up with. Now that gives us L sub I, but that doesn't give us capital L of x. All right, so to get that, we're just going to take each of the y coordinates, right, which is going to be 2, 4, and 7, and we're going to multiply those. All right, so we just take 2 and multiply it by this expression. We take 4 and we multiply it by this expression. We take 7 and we multiply it by this expression, and then we just add it up. And that's how we get to our Lagrange interpolating polynomial. Again, it's just a huge matrix. All right, we're just doing a whole bunch of matrix multiplication. That's what's really going on behind the scenes. All right, so with all that said, let's take a look at how we can work an example. Oh, and by the way, in the next, I just graphed the Lagrange interpolating polynomial and the 3 original points. Remember, we had 1, 2, 2, 4, and 3, 7. And notice that this polynomial is a perfect fit, all right, as it should be, because That's what a polynomial, interpolating polynomial does. All right. So in this example, remember our Bessel function we had in the Newton interpolating polynomial. Guess what we're going to do? We're going to do the exact same thing for Lagrange interpolating polynomial. Okay, so we're going to create a fourth order Lagrange interpolating polynomial. We're going to use the above points. And I'm just going to show you how to program that in MATLAB. All right, so what I'm going to do is I'm just going to go ahead and program the fourth degree polynomial, and then we'll do the rest of the stuff in another video. All right, so what I did was I already plugged in the x and the y, all right, which was the variables or the data points that were already found. So I went through, this is x, and then I just called this y this time instead of j1 or j, which I did in the previous video. All right. I also made a Sims variable x2. This is going to be the variable used. So the variable x in the Lagrange interpolating polynomial. All right, so I'm just going to use x2 instead of x because I already defined x to be the matrix or the original values. All right, so I'm going to define L1. All right, now notice that we have 5 points, so we're going to have 4 products. All right, so x2 minus x sub 2, right? We can't start with 1. Okay, remember with our Lagrange interpolating polynomial, this is static, that's just our x, and this is going to change. It's just going to increase by 1, but it can never be equal to the index of L. Right? And then we're going to divide that by x sub 1, right, minus x sub 2. Right? Now, I'm just going to run it just to show you that it's just going to give us a really basic polynomial for L1 so far, right? But we're going to multiply this, and notice I'm going to do matrix multiplication as I do this, dot times, and I'm just going to copy this, right? And I'm just going to change this to a 3, and I'm going to change this to a 3. Remember, all that does, the only thing with the Lagrange polynomial that changes is the second terms, and they just increase by 1 each time. And I'm going to change this to 5, and I'm going to change this to 5. All right, now I'm going to go ahead and expand this. And by the way, this is not the coefficient yet, okay? All right, but this is what we get, okay? It's just multiplied out. It's factored down a little bit. So that's our L1. Now we're going to get L2, right? And instead of copying and pasting, just to be certain I've gotten the setup correct, I'm going to just do the first one and just cut and paste. Now notice that I start at 1 this time, and that's cool because that's not equal to the index L. And this time we're going to have x2 minus x1. All right. Now, dot times, and guess what we're going to do? We're going to copy and paste. And I'll terminate this one with a semicolon. And the only things that we're going to change is we're going to change the second terms in each of the products, okay? In the fraction, just the second terms of each. So this is going to be 3, right? Because we can't have 2 because we're finding L2, right? And now this is going to be 4. And then this is going to be 5. All right, so it's not really all that difficult. It's just more tedious than anything, all right? And again, good thing I didn't give you like a 10th degree polynomial. All right, so now we're finding x minus x1. And now x3 is what we're going for because we're finding x3, and that's going to be x minus x1. And I'm just going to copy this and multiply it out 3 times more. And this is going to be a 5. This is going to be a 5. So I'm just going backwards. This is going to be a 4. And this is going to be a 4. And this is going to be a 2, right? Because we can't use 3. All right. And so L4, all right, and if you would just, if you find that you already get this, that's fine. You can go ahead and skip ahead until we actually get to the polynomial. So now we're going to have x4 minus x1. All right. And again, I'm just going to copy this. And the only thing we can't have is 4s now. So we can have 5, and we can't have 4, so we're going to have 3. And we should have 2, excuse me. I just did 3. So this should be a 3 as well. All right, so we have 5s, we have 3s, and we have 2s right here. Okay, there we go. All right, one last time. Oh, by the way, this should be dot times. So I think all of these are flipped. So I might have to change all these. So give me a second. No big deal. Good thing I caught that before we tried to run it. So this should be dot times. Okay, weird that I did it the first time and I didn't do the other ones. Okay, this should be a dot times. Huh. Strange that it's not changing. I thought I copied and pasted it correctly, but oh well. All right, and then this should be a dot times. Okay. All right. How come they're changing? Dot times, dot times. Maybe I'm just saying it, not actually typing it in correctly. Okay. So finally, L5. And L5 is going to be equal to x2 minus x1. And now we're dividing by x5 minus x1. All right. And close that out. And we have dot times. And just like we did for the other 4 interpolating polynomials. And I'm going to change this. Now, this has to be a 4, right? Because we can't have 5 because we're on L5. This is going to be a 3 and then a 2. All right. So now, this is just the setups for L1 through 5. Now, I'm going to get L. All right. And L, I'm going to start with L equals 0. All right. And this is going to be our function. Right? I'm going to make a for loop. So, and what I'm doing at this point, by the way, just to make sure you understand, is we found all the L sub i's. So now what we're doing is we're going to we've already multiplied out. So now we're just going to take the sum of all yi times L sub I. All right. And that's going to give us our 5th order or 4th order polynomial. Okay. So we're going to say 4i equals 1 colon, I'll just say length of x. All right. I'm going to say that L is going to be equal to L plus L sub I dot times y sub I. All right. In fact, we don't even need the dot times, but might as well just do it. All right. And we're going to end. All right. So now I'm going to run this just to make sure there's no syntax errors or logic errors. And it looks like it ran. So I'm going to do an fprintf. And I'm going to say that the 4th degree Lagrange interpolating polynomial is %s\n. All right, and I'm going to just say L. All right, so let's see what we get out of this. All right, so here it is. Looks like fun, right? All right, so that's our Lagrange interpolating polynomial, and this is the code as to how we get it. Now, I'm going to stop the video, and then we're going to pick up with determining whether or not it actually makes any sense by finding the error and then also plotting it on the Bessel function.